All right, everyone, get ready, because today we're diving headfirst into the universe, and we've got Stephen Hawking as our guide. Well, sort of. You all sent in your favorite bits from A Brief History of Time.
It's a classic, isn't it?
Totally. And we're going to unpack all the big questions about, well, existence itself. No pressure, right?
Right. What always blows me away about A Brief History of Time is how many people connected with it. To be a bestseller for that long, Hawking really tapped into something, that deep human need to understand where we fit into this whole cosmic picture.
It's true. It's like we're hardwired to look up at the stars and wonder what it all means.
Exactly.
And Hawking, he gets that, which is why he starts the book with that great story about the scientist and the woman who thinks the Earth is on a giant turtle.
Oh, yeah. And the turtle standing on another turtle.
Turtles all the way down.
Aw, sick.
Besides being funny, it shows how much our view of the universe has changed, right? I mean, for the longest time, we were sure that the Earth was the center of everything.
And it made sense at the time. That Earth centered view, the Ptolemaic model, it wasn't just some random idea. People were making observations and trying to create a system that explained what they saw.
Right? They had their whole system worked out.
Yeah, and it even made some pretty accurate predictions for its time. But then, boom, everything shifts. We go from an Earth centered universe to a sun centered one. Talk about a revolution.
It's a huge. I mean, it wasn't just about what orbits what, right? It was about how we see the universe, how we use observations to understand the world around us.
It's a complete upheaval, a totally new way of thinking about our place in the cosmos.
And like with a lot of scientific breakthroughs, shaking things up like that. Well, let's just say it doesn't always go over well. Poor Galileo.
Right. Talk about standing up for what you believe in, even when it means challenging those in power.
He's like, nope, the Earth revolves around the sun, and I've got the observations to prove it. And they're all heresy.
Exactly. But speaking of shaking things up, that's what Einstein did with his theory of relativity. And trust me, this is where things get really interesting.
Buckle up, everybody. Relativity is where our everyday understanding of, well, everything starts to break down. It's all about space and time, but not how we usually think about them. This is next level stuff.
Right, because Einstein comes along and basically says, time. It's not what you think it is. It's not this constant ticking clock that's the same for everyone everywhere. It's relative. It's affected by how fast you're moving and even the strength of the gravitational field you're in.
Wait a minute, hold on. So you're telling me that time isn't constant? So, like, if I hop in a spaceship and blast off at, I don't know, nearly the speed of light, time's going to be different for me than for everyone back on Earth.
That's the gist of it. It's this famous thought experiment called the twin paradox.
Okay, the twin paradox, go on.
So you've got these twins, right? And one of them takes off on a spaceship, traveling super fast, close to the speed of light, while the other twin stays here on Earth. When the spacefaring twin returns, get this, they're actually younger than the twin who stayed on Earth.
Whoa. Serious?
Seriously, time actually slows down for the twin traveling at such high speeds relative to the one on Earth. It's like something out of a sci-fi movie, but it's
Right.
real.
Okay, so time gets all wibbly wobbly, but then Einstein takes it even further, right? He doesn't just mess with time. He goes and combines space and time together.
You got it. He brings them together into this four-dimensional fabric we call space-time, which can be warped and curved by things like mass and energy.
Okay, I'm trying to wrap my head around that space-time. It's like, what, a giant sheet?
Imagine it like a trampoline.
Okay, a trampoline, I'm with you.
If you put a bowling ball on the trampoline, it creates a dip, right?
Huh.
And if you roll a marble nearby, it doesn't travel in a straight line. Its path curves because of the dip the bowling ball makes. That's kind of like gravity.
Okay, so it's like gravity is just a side effect of this warped space-time trampoline.
That's the idea. It's not some mysterious force acting at a distance. It's a consequence of the curvature of space-time itself.
Mind blown. So we've gone from turtles all the way down to a universe on a warped trampoline. What's next?
Well, where do we even begin? I mean, Hawking doesn't just want to talk about black holes and relativity. He wants to dive into the biggest question of all. How did the universe begin?
The Big Bang, the ultimate origin story. But it's not just a big explosion, right?
Exactly. We have to be careful not to think of it as an explosion like we're used to.
So no fireworks show at the beginning of the universe.
Not quite. It's more accurate to think of it as the expansion of space itself from a state that was incredibly hot and dense. Imagine a balloon. As you blow it up, the dots you drew on its surface, they all move farther apart. That's kind of like what's happening with galaxies in our universe.
So that's why it seems like everything is moving away from everything else because the universe is still expanding, even now.
Exactly. And here's where your excerpts come in handy again. Remember the cosmic microwave background radiation that Hawking talked about?
Right, that's like the baby picture of the universe, right?
Exactly. It's
Right.
this faint afterglow of the Big Bang, this sea of low energy radiation coming at us from every direction in space.
Wait, so this radiation is literally everywhere.
Everywhere. It's like a constant reminder of the universe's hot, dense beginnings. And get this, finding this radiation back in the 1960s was huge. It was some of the strongest evidence yet to support the Big Bang theory.
Okay, so we've got this expanding universe, evidence of a hot, dense beginning, and all this talk about warped space-time. Things are about to get really interesting. And by interesting, I mean kind of terrifying. All right.
Black holes?
Black holes, black holes, black holes. There's something about them, right? It's like just the name conjures up these images of like cosmic doom.
They definitely capture the imagination, that's for sure.
Yeah, and for good reason. I mean, they're like these extreme cosmic laboratories where everything we think we know about gravity gets like completely flipped on its head.
They really push the boundaries of physics, that's for sure.
Okay, so in the excerpts that you all sent in, Hawking talks about how they form when really massive stars die, right?
Yeah.
So the star is burning all this fuel, it's huge, and then it runs out of steam. But because it's so massive, its own gravity just takes over and it just keeps collapsing and collapsing and boom,
Oh,
black hole.
it's like the ultimate implosion. The gravity gets so intense, so strong, that nothing, not even light, can escape. That's why we call them black holes.
Because no light can escape. Okay, so there's this point of no return, right? The event horizon.
Exactly.
So once you cross that, you're not coming back. It's like a one-way door in space.
I like to think of it like, have you ever been too close to a waterfall? So you know you don't want to go over the edge because the water is just pulling you down. Kind of like that. Once you cross the event horizon of a black hole, there's no fighting it. You're going in.
No coming back. Okay, so what happens inside? Like, seriously, does everything just get crushed, like flattened like a pancake? What's going on in there?
Well, that's where things get really weird. See, at the very center of a black hole, at least according to Einstein's theory of general relativity, there should be something called a singularity.
A singularity. Okay, what is that?
It's kind of hard to wrap your head around, but imagine all the matter, everything that ever fell into that black hole, squeezed into a single point.
A single point.
A point with infinite density but zero volume.
Infinite density, but zero volume. My brain hurts.
It's a concept that makes even physicists scratch their heads. It's like
Mhm.
the universe is saying, this is the limit of what we know right here.
So we've got these massive things, these black holes,
Yeah,
that suck up everything, even light. And then at their heart, it's just a question mark.
pretty much.
But it gets even weirder, right? Because black holes, they're not even completely black.
Right.
That's where Hawking radiation comes in.
Exactly. Hawking came along and said, hold on a minute. These things aren't just cosmic vacuum cleaners. They actually emit something.
They emit what? Radiation.
Radiation. It all goes back to quantum mechanics, that weird world of the very, very small.
Quantum mechanics always stirring things up.
Right. So, down at the event horizon, near that point of no return, these strange quantum effects start to happen. And these effects allow particles to actually escape the black hole's pull.
Wait, but I thought nothing could escape a black hole.
It's a bit of a loophole, you could say. See, these escaping particles, they carry away a tiny bit of the black hole's energy with them.
So black holes are slowly losing energy.
Exactly. And since energy and mass are connected, remember Einstein? You ever
Right.
see one?
Yeah, right.
As the black hole loses energy, it also loses mass very, very slowly. It's like imagine a black hole slowly evaporating over billions and billions of years.
So even these cosmic monsters, they're not invincible.
Nope. They have a life cycle too. Okay, so we've talked about dying stars, points of no return, black holes that aren't totally black. But Hawking, he doesn't stop there. Remember, he's after the big picture, the theory of everything.
So time travel, is it just a sci-fi fantasy? Or could we actually, hop in a time machine and visit different eras?
Well, Hawking definitely didn't dismiss the idea of time travel. Remember those wormholes we were talking about earlier?
Right, the shortcuts through space-time. You're not
They
saying,
might not just be shortcuts through space, they could be shortcuts through time, too.
hold on, seriously, you're blowing my mind here. So you're saying these wormholes, these tunnels through the fabric of the universe, could also be time machines. How would that even work?
It's all about bending space time, right? Imagine if you could create a wormhole connecting two different points in time. Step through one end, and you pop out in a different era.
Okay, I'm trying to picture that, but wouldn't messing with time travel create all sorts of paradoxes, like in Back to the Future.
Mhm.
Going back and accidentally changing something, and then poof, the future's different.
Exactly. That's a huge question for physicists, the whole issue of paradoxes. One idea that Hawking talks about is the chronology protection conjecture.
The what now?
It's a mouthful, right? But basically, it suggests that the universe might have ways of protecting itself from paradoxes, even if we don't fully understand how yet.
So it's like the universe has a built-in safety mechanism to make sure time travel doesn't mess everything up.
It's possible. Maybe every time someone tries to change the past, something happens to prevent it, preserving the timeline as we know it.
That's both reassuring and a bit disappointing,
Mm.
you know. I wouldn't mind a little time traveling adventure, but okay, so maybe going back in time is a long shot. But what about the future? Could we travel forward in time?
Now you're talking. According to Einstein's theories, time travel to the future is definitely theoretically possible.
Theoretically. Okay, how? What do we need to do?
It all comes down to speed. The faster you travel, the slower time passes for you relative to someone who's standing still. Remember the twin paradox.
Right.
So imagine if you could hop on a spaceship that travels at like 99% the speed of light, you zoom around for a bit, come back to Earth, and everyone you know has aged decades while you've barely aged a day.
Whoa. So it's like hitting fast forward on everyone else's life.
Yeah.
Sign me up. But okay, as cool as time travel is, Hawking also dives into some seriously big philosophical questions, like the anthropic principle.
Ah, yes, the anthropic principle, the granddaddy of all why are we here questions. Why is the universe the way it is?
Like, is it just some random accident?
Yeah.
Or is there some deeper meaning behind it all?
Right. And Hawking explores different ways of thinking about it. One idea is the weak anthropic principle. It basically says that we shouldn't be surprised to find ourselves in a universe that can support life because, well, if it couldn't, we wouldn't be here to observe it in the first place.
It's like that old saying, the lottery winner is always surprised. Of course they are. If they hadn't won, they wouldn't be standing there holding that giant check.
Exactly. We're inherently biased to observe a universe that's compatible with our own existence. But still, even if it's not some grand plan, the fact that the universe is so perfectly fine tuned for stars, planets, and even life to exist, it's pretty amazing to think about.
It really makes you wonder, doesn't it? And that's what's so great about Hawking's work. He didn't shy away from the big questions, the ones that blend science and philosophy. He wanted to know not just how the universe works, but why it is the way it is.
He reminds us that science is about more than just equations and observations. It's about this deep human desire to understand our place in the cosmos. And that sense of awe and wonder, that's something we should never lose sight of.
Absolutely. So, as we wrap up our deep dives into a brief history of time, we hope you've had your mind blown a few times. But more importantly, we hope you're left with a sense of curiosity, a desire to keep exploring, keep asking questions, and keep looking up at the stars with that same sense of wonder.
Because out there, in the vastness of space and time, there are still so many mysteries to unravel, and who knows what incredible discoveries await us.
Until next time, keep exploring, keep wondering, and keep diving deep.